Hi guys, my name is Ernest and this is Ernest Sciences and Mathematics TV channel. Now today we are going to look at special properties of standard deviation, and of course this is going to be a collection of some of the properties that we have encountered in some of our discussions on the concept of variance. Now in this case we have talked about the concept of sample variance, which basically given using a particular formula for raw data given as the square of s, and this was given in terms of 1 over n minus 1, and I elaborated on this specific concept of n, and therefore that's going to be given as 1 over n, the summation of xi, which is going to be an arbitrary number of a particular variable x, and minus the mean given as such. So that one was given in terms of the square of those particular values. And I said that basically the I is going to be assuming values ranging from 1 to n given as such. And that one gave us the concept of a sample variance from a particular or a specific discussion on the concept of variance. Now in this case, I had mentioned that for us to try and evaluate this one, there was a specific condition which we had considered whereby the units of this particular distribution, of course, are going to be squared. And that is going to be problematic in a sense that, of course, we're going to have to maintain those specific units in their original form. So therefore, that one dictated that we find the square root of this specific value. And the square root of this particular value, therefore, was going to be given in terms of the square root of the summation of x minus 1, xi minus the mean. And then we are going to have this one, n minus 1. And this, of course, represented the value of s, which we defined as the standard deviation. And in this case, this was a sample standard deviation given in terms of s. Now, in this case, if we have going to consider this particular standard deviation, so this is going to be a standard deviation from the mean given as x bar. So suppose we are going to consider the standard deviation of or the deviation of this specific set of data from an arbitrary value given as a, we're going to represent this specific deviation using, of course, a representation of the summation of xi minus a, the square of that, over n minus 1, given as such, and that's going to represent a specific deviation of a particular value. So if we do a comparison of these two specific sets of data for the standard deviation, we're going to see that in this particular case, we can consider a case whereby this particular mean and a are not going to be the same. So we're going to have a not equivalent to 0. So for a particular set of data, then therefore we're going to have a special property of the standard deviation, in a sense that if we try to compare these two values for the standard deviation, considering the mean and that arbitrary value, we're going to have a special property which I'm going to mention, whereby we're going to have this standard deviation given in terms of so this is going to be the first property whereby we're going to have this standard deviation given as a summation of xi minus the mean, the square of that, all over n minus 1 is smaller than the value we're going to obtain from the summation of xi minus a, the square of that, all over n minus 1, whereby the value of a is not equivalent to the mean as I've mentioned, and therefore this is going to be one of the special properties that we're going to see, that if we try to find a standard deviation of this particular nature and consider value of a, then therefore the value of this specific evaluation is always going to be greater than this one, and this is going to be one of the special properties of the standard deviation. Now if we consider for a normal case, or a normal, of course, a case whereby we're going to see that this is going to constitute a symmetric distribution. We're going to learn about this one in our subsequent videos. So for a symmetric distribution, we're going to have some of the conditions which are going to be seen for a particular set of data, in a sense that for a particular set of data, whereby we are going to see this one considering the concept of this is standard deviation, we're going to see that a particular percentage of a set of data is going to fall within that particular category, considering the percentage of, or considering the standard deviation, in a sense that for a set of data, let's assume, so for a set of data, it's going to be, only representation of that set of data is 100%. So suppose we have a particular percentage, then therefore we're going to consider a particular case. Now, from various evaluations, it has been confirmed that 68.27%, which is an approximation, falls within a one standard deviation. Falls within one. I'm going to give this one in terms of a summary form. So for n set of data, which is from a symmetric distribution, 68.27% is going to, of course, have a one standard deviation of the mean, implying that we can have an algebraic representation of this specific relationship, and therefore that is going to fall within this specific category, whereby we're going to have this one, the mean minus one standard deviation, or the mean plus one standard deviation. So in this case, it implies that if you 68.27% of a particular data, of course, is going to fall within the values of one standard deviation of that particular mean, then therefore we're going to consider either the positive standard deviation for one value or the negative standard deviation for one value. And this is going to constitute a particular relationship for the second characteristic. So in this case, of course, we can consider other specific values of perhaps one, two, or three standard deviations. Now, in this particular case also, we're going to note that from specific evaluations which have been done, approximately 95.545% of this specific data from the symmetric distributions are going to fall within two standard deviations. So this 95.45% of data from values of data from this symmetric distribution are going to fall within two standard deviations of the mean. And this can be represented in terms of, because of space, I'm going to do away with this. So this is a continuation of the second characteristic, whereby we're going to have this one represented as x minus, or x, which is going to represent the mean, minus 2 standard deviation, or x, which is a mean, plus 2 standard deviation. So in this case, this is going to cater for the concept of 90 for a symmetric distribution or a normal distribution. 95.45% of the data values are going to fall within, of course, two standard deviations of the mean, and this can be represented in this particular case using this above representation. Now, of course, we're going to see that also, if we're going to consider also perhaps a third standard deviation, we're going to see that 99.73% of data from this symmetric distribution, data values from this symmetric distribution are going to fall within 3 standard deviations. So this is going to be 3 standard deviations of the mean given in that particular case. So as well, we can have a representation for this having this 3sx minus or plus 3s given as such. And this, of course, a specific relationship that we have seen for the symmetric distribution. We're going to try and see what are some of the, of course, concepts which are going to be developed from this, especially on the Egyptian's theorem, which we're going to look at in our next discussion. So in this case, in a summary form, I've said that we have special properties of standard deviation, considering the concept of the mean and a particular value or arbitrary value of A. We're going to see that this specific evaluation for the mean is going to also be always smaller than an arbitrary value that we may consider for the standard deviation of a particular value of A given as such. And secondly, I've said that we're going to consider the case of a specific set of data whereby a particular percentage is going to, of course, fall within 1, 2, or 3 standard deviations from the mean. And in this case, if we try to consider a set of data, then therefore we're going to see that 68.27%, of course, is going to, of our data values are going to fall within 1 standard deviation of the mean, and 95.45% of data values are going to fall within the two standard deviations of the mean, and this can be represented using this particular illustration. And then 99.75% of the data values are going to fall within 3 standard deviations of the mean given as such. So I hope we're going to, of course, comprehend those specific ideas from the special properties of the standard deviation, and therefore we're going to find them being applied in various discussions as we proceed. So that is it for now, guys. Kindly check our description boxes for various links of other videos, and check a link for the subsequent video where we're going to see one of the applications of this, of course, on the Jepchai's theorem in our next discussion. So that is it for now, guys. Bye, God bless you. Catch us in our next video.